Lecture 3.2, Predictions and Extensions of the Ideal Gas Law. The ideal gas law, as it stands, has gas particles that have no volume. And therefore can and not collide with each other. Clearly, this is not realistic for real gases. So here we go. We start with the question that says, how does one extend ideal gases to real ones? Real gases clearly have a volume, and they do collide. So here's what we have to do then. If gas particles were to collide very infrequently, they would have small but non-zero volumes. Now, it turns out that the ideal gas can handle that to a high degree if you cherry pick the gases. Okay, so you got to be really careful. Let me say that one more time. If you cherry pick the gases, then the ideal gas law will hold to a high degree. So, in other words, the bottom line is if one uses the ideal gas on real gases, they must have low densities. That's a big key. They gotta have low densities. So let's go from here. The biggest take away from deriving the ideal gas law was it led to the internal energy function. And that's huge, right? We now know that the internal energy, which is what we mean by K micro, and then we have N times K RMS. We already said that those were two different kinetic energies. This has to equal N CV delta T, where for ideal gases, CV is equal to 3/2 R. So in some sense, let me move this up. In some sense, we clearly, let me be careful with the word clearly, we clearly see the guts of internal energy. We clearly see the guts of internal energy as the heat capacity at constant volume. So what did we say before, right? Once again, we said that heat capacity tells us how a a gas distributes its kinetic energy. Remember, ideal gases don't have potential energies. So we have no right up to now to not talk about potential energies. So what do we mean by an ideal gas? So here's the definition. So when we say the word ideal gas, the word that's commonly used is called a monatomic gas. So monatomic and ideal are one and the same. So here's what we know. A monatomic gas has 3 freedoms of motion. So that word is important. By looking at the motion, it tells us how the CV function is going to behave. But we don't call this freedoms of motion. The language is called degrees of freedom. A lot of textbooks use F as the number of degrees of freedom. I learned DOF. So the freedoms of motion is called the degrees of freedom, abbreviated DOF. Oops, that's not what I wanted to write. So let's try that again. That is the only possible motions of a monatomic. And by the way, monatomic also means point particle, or so that means here, so if I have a gas particle, here it is, there's only 3 ways that it could move. It could move in the X direction, the Y direction, and the Z direction. So then that tells us here is that degrees of freedom are then 3. The heat capacity exactly tells us this. Look at how we define the heat capacity at constant volume. We said that it was 1/2 plus 1/2 plus 1/2 times R. And so we get this factor of 3 because of the degrees of freedom. This is not new. So once again, the heat capacity at constant value tells us how the internal energy distributes the kinetic energy. So let me scan up here, and here we go. So now let's look at the predictions for a monatomic. Remember, if I say the word monatomic, I mean an ideal gas where the units are in, you know what? Let's not do that. Nope. Sorry. I think the right question to ask, what is an ideal gas? And we've already defined it that this is a monatomic gas. What does that even mean? So it turns out only a handful of gases are monatomic. And the ones you want to pay attention to are the ones on the periodic table. There's some exceptions, but this is what the periodic table. So when you think of an ideal gas, the one element you should be thinking about is helium. Helium is by far the best ideal gas. Now, these others, it turns out that it's more complicated. Okay, it's more complicated. So let me write, a little bit here just to make sure that we're clean on this. So the noble gases. You know what's interesting about the word noble gases? They were actually discovered by English, and maybe because of the nobility, they called them noble gases. But anyways, the noble gases as well as as well as hydrogen, nitrogen, and what's the other one? I believe it's oxygen. We have to Google this. I'm pretty sure these are the 3. Are especially good approximations to monatomic. And the reason why is mainly because, so when you look at the Nobel gases, I can only say this with the Nobel gases, it's mainly because their outer shells are full, which means that they're extremely stable and they form no bonds. Now, note, hydrogen, nitrogen, and oxygen, they do form bonds, but they still work pretty good as an ideal gas. Okay, so now that we've talked about that, now we have that. You know, I don't know how much to actually say here. There's a problem with nitrogen, argon, and krypton. It's because they're large. Their volumes can't be ignored. So in some sense, what ends up happening is you get this terrible equation called the van der Waals. I forgot how to spell one. I think that's the way you spell van der Waals. Effect comes into play. And that's because they're large. Not the case for helium. So now let's compare theoretical and experimental measurements. Well, there's two pieces to this thing. We need to talk about the theoretical, and here's the theoretical. So the theoretical says that CV is then 3/2 R, 3/2 R, and that value turns out to be 12.5. By the way, all of the units I'll write at once is joules per mole per Kelvin, but I'm not going to include the units in any other thing. Of course, CP is 5/2 from what we calculated, and this is 20.8. Then, of course, there's the difference between these. So by definition, this is the gas constant. And then there's this adiabatic constant, gamma, which is CPCV, which is 5/3 or numerically 1.67. So these guys are the theoretical predictions right here. Now remember, we have cherry-picked these values, okay? So now we have the experimental. Okay? Like, for example, if you applied this to lithium or beryllium, these values are not nearly as good. But I have a table here that I'm going to share with you that I've set up that looks like this. So what you're seeing here, in green here, you can clearly see that right here, these are the predictions. And then over here, these are the experimental values. And when you look at them, again, you cherry picked your things because you want to make it so that it doesn't interact. That's the key thing. You can see that the values for CV are really good, which then means CP has to be really good. And you can see it's pretty close with the values of CP minus CV and very close with gamma. So you can see here really clearly that the predictions are quite good. You know, for these hand-picked values. And they have to be hand-picked values, right? They have to be wait. I said values. I should say hand-picked elements. They have to be, because to be an ideal gas is complicated. Now, applying the ideal gas law to more complex molecules failed terribly. And that should not be a surprise. Why is that not a surprise? Ideal gases are not diatomic or polyatomic. So if I put in this table, you can see here is that in this case, this is what we call a diatomic. So what do we mean by a diatomic? That means we essentially have two molecules that are kissing. And then these other ones are polyatomic, and those are more complicated. But what they typically talk about, you know, polyatomic, this is the standard picture that people use. They'll go, okay, here's a polyatomic molecule. And so in this case, they typically show 3. It doesn't mean that you have 3 molecules. So in this case, you could see that the values are way off, and these values are also way off. But I want you to really make a comparison here. I think that's the important point. Note the CV values for diatomic are really close. And I would say that that value is around 21. They're really close in value, but not, the polyatomic gases. And that's not a surprise. Of course, they shouldn't be. So what we're really saying here is that roughly, I could say that the CV for diatomic is about 21 joules per mole Kelvin, and CV of polyatomic, which is a really rough value, I'm going to say is about 28 joules per mole Kelvin. So here's what this does. So when you're looking at how close, again, look at the values, look how close these guys are, right? They're really close to 21, except hydrogen. But the other ones are really, really really close. So then, as you could imagine here, is that this begs the question, can the ideal gas law model be extended? To include diatomic / polyatomic gases? That's a reasonable question. And what you're going to see here is this, that the answer is a big yes for diatomic, but polyatomic has limited success. And there's a really good reason why. And then we get to the very famous equipartition theorem of classical statistical mechanics. And that's where the kinetic theory of gases come from. Excuse me. Here's what we know. So I'm gonna start off easy with the equipartition theorem, and then I'll get a little bit more complicated. So from classical statistical mechanics, the equipartition theorem states in a nutshell, it says that in thermal equilibrium, now that's important. Thermodynamics can only be calculated in equilibrium states. In thermal equilibrium, and this one's tough, energy is shared equally among all of its degrees of freedom. So all energy is shared equally according to their degrees of freedom. Now, ideal gases do not deal with potential functions. They deal with K micro. So in other words, that is, K micro is divided equally, which is what I said already, among all of its independent kinetic energy parts. Well, things are not so simple. So here's a restate of the equipartition theorem. It says any degree of freedom, such as velocity, we know kinetic energy is quadratic in velocity, or position. So as soon as you say this, you know you're talking about kinetic energy. Here, you know you're talking about potential energy. That appears, okay, let me be careful now, appears quadratically in their energy contributions will, on average, contribute 1/2 kBt to the heat capacity. This is a mouthful. Okay? This is a mouthful. And so I'm going a little bit beyond the scope of this course, but that's what it actually says. So let's go look at this and what do we mean by this? Okay, so let's go back to monatomic / ideal gases. So what do we know about monatomic ideal gases? These have 3 degrees of freedom. And so that means each degree of freedom gets 1/2 kBt. So in other words, if I have gas particles, and I could imagine that one can move in the X, one can move in the Y, one can move in the Z. Therefore, the internal energy, because of their motions, which is K micro, of course, is then going to be N times K RMS, but we already know what this means here. This is 1/2 mv RMS squared, but this is in 3D. But the key thing that you want to pay attention to is that look at this guy right here. This guy is quadratic in the internal energy and speed. So then that means that because we have 3 of these guys, then we have 1, 2, 3 kb, kBt, or we can write n of 1/2 plus 1/2 plus 1/2 RT. In other words, when I look at the definition, we then say here's that CV is then going to be the degrees of freedom times 1/2 R. So in this case, we get 3 times 1/2 R, which is a value that we already knew. Okay, that was a value that we already knew. Let's go to diatomic, right? So if I look at diatomic gases, what do we see here? Well, these have 3 translational motions plus 2 rotational motions. Let's draw them out. So if I look at if I'm looking at diatomic molecules, then I can see that I could have something like this. Here's my diatomic molecules. So that means here is that I have Vx, Vy, Vz, plus there's 2 other motions. So if I have a diatomic molecule like this, Or like this, there are two axes that they can rotate about. They can rotate about this axis, and they can rotate about that axis. So if I look at this thing, this guy is the polar angle, so that's going to be omega theta. Oh, no. This is the azimuthal, excuse me. And then this omega that rotates like this, oh, I got them mixed up. So this is the, no, this is the azimuthal, so that's theta. And then this guy, phi, is the polar angle. So what you're seeing here is that there are 5 freedoms of motion. So in other words, their degrees of freedom is, of course, 3 plus 2, which is 5. So what does the equipartition theorem says? So the equipartition theorem states, look at the internal energy. Any term that's quadratic gets 1/2 kBt. So if I look at the internal energy, now I look at K micro, there are 2 kinetic energy terms. There's the translational kinetic energy plus the rotational kinetic energy. So that means is that if I have n particles, I have 1/2 m v RMS squared. There's the quadratic term. But now I have additional rotational terms. In other words, I could have 1/2, let's call this I1 for its moment of inertia, because it's rotating along a different axis. So this will be, let's say, the azimuthal angle. And then I have the polar angle that looks like this. And you can see here is that this guy and that guy right there, they're quadratic in kinetic energy. So then that means here that each of these guys gets 1/2 kBt. So now if I look at this thing, this is then going to be n, and then it's going to be, so translational is 3/2. Then each of these gets 1/2 kBt, or I could write this as n 5/2 kBt, or I can write this as n 5/2 RT. That's what the equipartition theorem. So then this tells us here that now CV for a diatomic gas is now 5/2 R. So what are the predictions and experimental values for diatomic gases? Let's go look at that. So here I go. So here's my, how do I say this? So let's compare them. So here's the predictions. So what are the predictions? I have CV, which is now 5/2 R, and this is 20.8 joules per mole Kelvin. I'm going to drop the units. So I'm only going to focus on CV, CP, and gamma. So then if I look at CP, this guy is now, remember it's CV plus R, so this gives you 29.1. And gamma is unitless, so this is Cp over Cv, you get 7/5, which is equal to 1.40. These are the predictions right here. How well does it compare to? So this guy right here is our experimental values. So what I'll do here is that I have a table already set up, and it looks like this. So you can see here that these guys are diatomic. Okay, they're diatomic. And when you look at the values, look at the prediction, 20.8. Oh, this is fantastic. Look at CP, really good. You can see the difference is almost right on the ideal gas value. And then look at that one, this gamma is so good. However, these are cherry-picked. These are cherry-picked. So what do I mean by cherry-picked? Because if you apply this to all of these diatomic gases, you're going to see that there's a big failure. So the term cherry picking comes from when people harvest cherries from a tree, the cherry picker only takes the reddest, ripest fruit. If someone looked at all of the fruit that the person had picked, they might think that all the cherries are red until they went to the tree and saw lots of pale, unripe cherries still on it. These are hand-picked values, but they represent the best options for a diatomic ideal gas. So they do really well, right? They do really well. Then we get to the polyatomic. So when we have a polyatomic, what's separate between a monatomic and diatomic, is that polyatomic molecules have oscillations. And by the way, a lot of the times you'll hear me say the word, they have vibrations. They're oscillating back and forth. They're vibrating back and forth. That increases the degrees of freedom. So what I want you to do is that I want you to imagine a one-dimensional oscillator. So what do I know about a one-dimensional oscillator? Well, I could imagine that I have a spring system that's connected to a cart like this. So if I connect it to a cart, maybe the cart is orange and it's connected between two springs. And as soon as I displace this cart, it's going to oscillate back and forth. Molecules can do the exact same thing. So in this case, I imagine that I have a molecule right here. And that's the most probable location, is at the equilibrium point. So what you're seeing here is that this molecule kind of spreads out, right? So if I'm thinking about this, what I'm seeing here is that these guys, when this gets to the equilibrium point, let's say that this is the equilibrium point, here's what we know. The equilibrium point gives you maximum kinetic energy. And when you're farthest from the equilibrium point, you get maximum potential energy. A good picture to have in your mind would that be of the potential of a spring. So if I look at a potential of a spring, it looks something like this. Oops. Let me start from this direction. Let's say it goes to right here. And what you're seeing here is that there's this energy well that doesn't allow particles to move. So if I look at this thing, I could have maximum kinetic energy right here because it's at the bottom of the well, or I could have maximum potential at the endpoints, and that's because it has maximum displacement. So if I look at here, I know that K max is maximum right there. Here, I know that U max is that, but then K here is absolutely zero. So if I look at an oscillator, the energy of the oscillator looks something like this. It has both kinetic energy plus potential energy, spring potential energy. And when you look at this thing, we can say here is that this is 1/2 mv squared plus 1/2 k squared. Guess what? Look at this. Look at that. They're quadratic in the energy expression. Now, I'll get to that in a point here, but as a visual aid, how do you spell visual? Yeah, visual aid. Oops. Imagine a diatomic molecule vibrating / oscillating back and forth. So now all of a sudden, what you're seeing here is that is a one-dimensional oscillator, right? That's a one-dimensional oscillator that's now going to oscillate back and forth. So there's a couple of things that we should address here. Unfortunately, polyatomic molecules are quite complicated. For example, look at the oscillation modes of water molecules. Oops, that's not. I mean, here's just a few. These oscillations, and I'm just going to focus on one. They typically call this type of oscillation, this is a stretching oscillation. And again, I'm only talking about one. So if I think about water, I imagine that this is my oxygen. And when I look at this, I have 2 hydrogens. And what I'm going to do with these hydrogens here is that I'm going to imagine that they're on springs. So guess what? You can have oscillations like this that get quite complicated. In other words, here's what you can do. You can get the oxygen to oscillate up and down, as well as each of these hydrogens oscillating back and forth. This is typically what they call symmetric stretching. But that doesn't mean that that has to happen. There are oscillations that look like this. It turns out that one of these guys now is fixed, while this hydrogen is the only one that's oscillating. Or I could have the other direction, right? This is asymmetric. So then this one is fixed, and then this one oscillates back and forth. I mean, it's yeah. Then there's, by the way, here's another one here, because you got to go through all of the possible perturbations of the oscillation. And what happens here, there's a very famous oscillation, especially with like if you look at the cesium clocks and stuff like that, the hydrogens are fixed, but now the oxygen actually tunnels through the two hydrogen atoms. It's pretty, quantum mechanics is absolutely beautiful. There's no doubt. So what am I saying here? This changes the degrees of freedom quite radically, because they're possible oscillations. And according to the partition theorem, each mode gets 1/2 kBt. Okay. Unfortunately, things get really murky here. It's really hard to see what's going on. Most textbooks and lower division physics courses do not look at the contributions of potential energy. They're neglected. That is, most of the time, except in higher level physics courses, potential energy is ignored. And only focus on the quadratic kinetic energy term. So guess what? That's a big deal. So as you could probably guess, polyatomic gases don't really follow this extension that well. So that means polyatomic gases at this level only focus on the vibrating kinetic energy. The vibrating kinetic energy contribution to heat capacity. So here's what they say. So if you do that, if you look at the degrees of freedom, you really have then what? You have Vx, Vy, Vz. These are all quadratic. We have two rotations, which are quadratic. And then you have some velocity that has to do with the vibration of this. So they say it's 6 here. So that implies that CV for polyatomic gases is then 6 over 2R. And you can see here is that this is a gross neglect. Okay, a gross neglect. But that's what we're dealing with. So now what I want to do here is that I want to look at the values that we have right here. So as one can imagine, the extension to polyatomic is not going to go well. So here we go. Here's the predictions. We have CV is equal to 3R. That numerical value is 24.9 joules per mole, Kelvin. CP is equal to 4R, which is then 33.2, and then gamma is equal to 4/3, which is 1.33. So now let's look at so these are the predictions. Now let's go look at the experimental values. So here's my table, and it looks like this. So what you're seeing here is that, look at the values. The theory predicts 24.9, and look at these values here. Look at the difference between these. So if you look at the differences, it ranges from, at best, 8.5%, and then these are 26%. Again, remember, these are cherry-picked to show the best values. They get worse very, very quickly here. And if you look at the CP value, look at that. It's not doing so good. You could see that the prediction of the ideal gas constant, unfortunately, and then you could look at gamma, looks pretty good here. So let's start to wrap up this thing, and then we haven't talked about any of the physics yet. So here's what we could say in summary. So in summary, we said that in thermal equilibrium, each degree of freedom has an associated 1/2 kBt per molecule for kinetic energy zoning, right? So in thermal equilibrium, I hope I can remember what I said right now. Each degree of freedom has an associated kinetic energy equal to 1/2 kBt, not potential energies, per molecule. Where we said then that then the internal energy, which is also K micro, is then going to be N times the degrees of freedom times K RMS, which then tells us then that this is then N CV delta T. You know what? I don't need this. This is what I need. This is what I want. Everything contributes to CV. This is what I wanted to say, not what I initially wrote. So then here we go. If I have monatomic, that tells us that CV is 3/2 R because we only deal with translational. If I have diatomic, we have 5 degrees of freedom. So therefore, that tells us then that CV is equal to 5/2 R. And then finally, if we have polyatomic with limited success, then our CV here is then 6R, 6/2 times R. That's what we're being told right here. So now, what I want to do is that I want to now do the interpretation. I think there's a T here. Interpretation of the equipartition results. What does this all mean? Here's what we started with. So suppose, remember, we got to go to CV. How did we define CV? So I want to suppose isochoric heating is done so it only changes internal energy. Internal energy. Right? So I imagine that I have a container of gas. Here's my container of gas. And so when I look at this gas container, what I'm going to do here is that I have an ideal gas inside of here. Right? Here's my ideal gas. Now what I'm going to do here is that I'm going to add heat to this, and this thing is kept at constant volume. Right? So here I have heat, and the way I keep it at constant volume is that you can see that it's a fixed value. So I'm only going to focus on heating. I don't really have to think about a lot of this here. So now here's what I'm seeing here. Here's my graph. So if I think about constant volume heating, then this one moves from state 1 to state 2. Now, if I have constant volume heating, that means here is that I'm going to add heat in this process. So clearly the volume is fixed, but we're seeing that the pressure on this guy changes as I do this. And what do we know? We know that the internal energy is proportional to K translational. In other words, K RMS. It's also proportional to the rotational, and it's also proportional to the vibration. Okay, so the first thing that I want to do here is that I want to start looking at how do I say this? Let's start off with monotonic. Of course we are. So here I go. So the first thing that I'm going to do is that I'm going to look at heating a monotonic gas. What does it mean when I heat a monotonic gas? So these are point particles with only translational components, right? Vx, Vy, Vz. So what this means here is that all heating goes into increasing K translational. And of course, that's proportional to temperature. So let me share my screen with you. So if I share my screen with you, here's a monotonic gas. And you could see that they only move in translational modes. So I just took an image of this thing. So let's go back to my picture here. So if I look at that, let me transfer the image back. I have this image. This is my image right here. So now let's look at what the heating does. So here's I have my heating now. So I look at this guy, and I'm going to say that these guys are 3 squares big. So this is heating done at constant volume. So what is all this heating going to do? It's going to change kinetic energy, right? And as it changes kinetic energy, I'm going to say that the way it changes kinetic energy is that it all goes to K translational. In other words, it is not sharing the heating with any other component but K translational. So what I'm saying here is that the change in the translational kinetic energy gets all the heating, all the heating, the heat energy, and quickly changes temperature. So the word here is quickly. I think we should really emphasize the word quickly. So now what we want to do here is that I now want to go look at, in this case, just like I said up here, look what I'm going to do. I'm going to repeat myself. So we're heating diatomic molecules now, or diatomic gases. Now, what do I know about diatomic gases? These have both translational and rotational components. So when I look at these guys, they have Vx, Vy, Vz, omega theta, omega, the polar angle. So let's go back to my applet now. Let me bring this up. So I'm going to go do a new share. And when you're looking at these, look at when I go to a diatomic gas. You can see that not only do they have translational, they also have these possible rotations. So when I go back and I look at this thing, if I copy my image, then I have this situation. So now what you're seeing here is that the equipartition theorem, the not equilibrium, partition theorem says that these 5 degrees of freedom get 1/2 kBt each. So let's look at this thing here. So that means then if I have 100% of the energy of the heat and I have 5 degrees of freedom, that means each degree of freedom gets 20%. So then that means here is that the change in translational kinetic energy, since it has 3, gets 60% of the energy, whereas the rotational kinetic energy, there's only 2, gets 40%. So look what happens. So if I draw my bar diagram as before, I then have this guy right here. Here's QV, and I need to keep it at 3 squares. So when I look at this, what actually happens? Well, it distributes the energy. So when I look at K translational, it's going to get a little bit more than half. Let's say that this is 60%. This is K translational. And this is going to get 60%. The other one, which is less than 50%, it's at 40%. Let's say that's 40% right there. Then this tells me that this goes to the rotational. Key point. K translational gets less of the heating and look what happens up here with the monotonic. Gets less of the heating, and what happens? And it changes temperature slower. And that's exactly what we talked about when we were dealing with, like the pie crust versus the pie filling. There was a change in how you deal with that. Now we're heating a polyatomic gas. Well, let's look at that. These have not only translational, not only rotational, and now they have vibrational components. So that means our degrees of freedom have now increased. There's now 6 of them. So again, if we go back to the applet, just to make sure that you're seeing this, I could now go in and talk about water. Look at the water. Here, you don't see the vibrations, and it turns out it's because the heat's not high enough, but they're there if you heat it sufficiently. So now, taking this guy, I'm going to go back to my screen, and let me get the image here. So this is the image that I have. And so I'm going to follow the same thing here. What does the equipartition theorem says, right? So it says here that I now have 6 degrees of freedom. Each get 1/2 kBT. So if I have 100% of the heating, now I have 6 degrees. It turns out that this is 16.7%. So then guess what? When I look at the K translational, they actually get 50%. Note that 50% is less than 60% when compared to the diatomic. K rotational gets 33%, and K vibrational gets 17%. So now, again, let's deal with the bar diagram. So if I look at the bar diagram, I then see here is that I have this kind of heating. And what is this heating going to do? It's going to change the kinetic energy to how? Well, it looks like this is about half right there. So I'm going to say half of it goes to K translational. About a third of it goes to K rotational. And then 17% gets K vibrational. So what you're seeing here is that now when you look at this guy, you could say that K translational gets even less of the heating and is slowest to heat up, to change temperature. So when I put this all together, I could now say that in summary, what am I seeing? In summary, I see that CV of polyatomic is the largest. CV of diatomic follows. CV of monatomic. So you're seeing here is that the higher CV implies you have more ways to store internal energy. So therefore, it takes longer to change its temperature. In everyday language, we say it takes longer to heat up. That's not correct. It's change the temperature. And then if you have a lower CV, then of course there's less ways to do that. So most of it goes into K translational. So therefore it's shorter to change the temperature of that material. Now, as you can see, temperature is more complex than just a measure of hotness and coldness. Temperature gets complicated. In fact, it gets a lot more complicated. So let's say that you're in the know. Maybe you've had some chemistry background. When you start to look at atoms, they have energy levels. The more energy levels you have, the more degrees of freedom you have. Furthermore, you also know that electron spin is about the magneticness of a material or of the atom. That also increases the degree of freedom and changes its temperature. It's more complicated. Temperature is pretty involved. I remember when I was an undergraduate and I finally learned the meaning of temperature, I went like, oh my gosh, I really had it wrong for a long time. So to leave you, I thought the previous example was good, but let's try to do this here. I'm going to give you a silly analogy. But this silly analogy is accurate. Now, suppose we have a bucket full of water whose volume is 3 filled glasses. So what I'll say here is one analogy is that I'm going to say that the water is the energy, the amount of water in a glass. So then the degrees of freedom I'm going to define by the number of glasses. And then finally, the amount of water in a glass now equals the temperature, which is connected to the heat capacity. So what I need to do here is that I'm going to draw a series of pictures here. So here I go. So I'm going to start off with 3 glasses. And I'm going to cheat and I'm going to start copying. So here's 1 glass. So what I want to do here is that I want to copy this glass. Okay, so I'm going to copy this. So here's 3 glasses. So this is the total amount of water in a bucket. So to try to do things faster, I'm now going to create a series of other glasses. So there's this glass. Now, not that they're all full, but I'm going to have to modify these. And then I'm going to copy all of these. Oh, what just happened? I don't know. Let me go back here. Let me see if I can copy these now. My computer is really slowing down. Okay, I'm almost set here. So now I got to multiply all these. So you could imagine I have a bucket. Here's my bucket. Let's say that I'm going to draw my bucket right here. And this bucket full, it contains, it's a bucket of water. And what I'm going to do here is that I'm going to pour water into these glasses. Now note, if you're monotonic, there's only 3 glasses. If you're diatomic, you have 5, and if you're polyatomic, there's 6. So now what I'm going to do here is that I got to go clean these guys off. See if I can not erase. So here we go. That's perfect. So now what I'm going to do here, this guy is monatomic. And what you're seeing here is that I was able to pour all of the water into these 3 cups. Now, if I go to diatomic, it's not 3 glasses, it's 5 glasses. So what happens? These glasses don't get full of water. I'm distributing this amount of water equally into these 5 glasses. Now, if I go to polyatomic, I have 6 glasses. So what that means then is I get even less water equally distributed to these 6 glasses. So what does this tell me here? This guy gets this has the most water. So then the analogy is that it's going to heat up the fastest. And it heats up the fastest because it's the temperature is the amount of water. This guy, this has the least water. So that tells me here that it heats up. Oops. Heats up the slowest. And you could see that diatomic is in between here. So to give you a sense of this, I want to now play a video here. I want to watch. How do you spell watch? Watch a video that compares K-translational. Remember, that's also the speed that we want to pay attention of diatomic and polyatomic gases. So we expect, by the way, this is at a temperature of 500 K. So what we expect here is that the RMS speed of the monatomic, since it all gets translational energy, that should be the fastest moving particles, followed by its RMS speed for diatomic should be greater than that of polyatomic. So let's watch the video. So what you have to do here is that you have to compare each of the gases. And so what I did here is that I put videos that look something like this here. So here it goes. So this is in the link here. So this is a a monotonic gas. Pay attention to the speed. Look at the speed of the gas particles. Now look at the diatomic, same temperature. See how they're moving slower? Because they get less translational. Now look at polyatomic. They're slightly moving slower, even though the temperature is the same.